some algebra skills, graphing skills, stuff, again, that you need to be very comfortable with before we get too deep into this section, because it will be so to your advantage to know this and feel confident with it as you're going into these limits. Okay, so we're looking at section 2.2, and this is called the limit of a function. And we really don't get to the true detail of limits even in this section, but we start to, and limit laws. Okay, and before we get too far into it, just a little bit of an algebraic review again, because when you start doing limits, it gets deep, and if you can have a vision in your mind of what the graph of the curve looks like before you have to do the limit, it'll be so much easier. Okay, so let's just talk a little bit about rationals. Let's take a look at these functions and make certain we remember what they look like and just a little detail about them. This is a rational function. I'm certain you've heard the word rational. Rational means it's a function that's a fraction, more or less. And the minute you hit rationals, you're thinking vertical asymptotes. You're thinking, what makes the denominator 0? This is a problem. This creates vertical asymptotes and gives me weird-looking graphs. So in this case, in your denominator, you recognize that dare x be negative 3, this graph is going to go wild because it's going to have a vertical asymptote because it's undefined there. So when you graph this, you have a vertical asymptote at negative 3, which we put in as a dashed line. And then the graph of this thing looks like this. Okay, so you have when you have a rational function, a function that's a fraction, be very prepared to hit these vertical asymptotes. And this one, we usually use the notation vertical asymptote. This has a vertical asymptote of x equaling negative 3. Now, still talking about these rationals because they love to use these problem situations when we're finding limits in the near future. Here's another example. Suppose we have a function that looks like this, another rational, and it's x squared plus 5x plus 6. There is bound to be a vertical asymptote. There's bound to be an x value that causes this rational to have a 0 in the denominator and be undefined. Does anyone know what that number or numbers are? Negative 2 and, hold on, is that right? Negative 2 and negative 3, right? Okay. So how in the world did those numbers happen to flash across my head and yours? When you factor this trinomial, you factor it into an x plus 3 times an x plus 2. Very quickly, when it's in the factored version, you can see if x is negative 3, I've got a 0 in the denominator, or if x is negative 2, I have a 0 in the denominator. Those cause huge problems. Those are causing vertical asymptotes. So here I have two vertical asymptotes. One is occurring at an x value of negative 3, and the other is occurring at an x value of negative 2. So we come in here to try to sketch this one to get a vision of the graph, because I promise you they're going to ask you, they're going to start computing limits at these problem situations. Over here at negative 3 is a vertical asymptote, and then also at negative 2. I'm going to, I didn't mean to put those so close together. Okay, there's your two vertical asymptotes. So what in the world does this graph look like? Well, to be honest, what I would do is I'd pull it up on the calculator and take a good look at it. Where is my calculator? So here comes the virtual TI. And I'm certain, well, this will be a good review too to get you comfortable on the calculator. This is a really nice software package if it would load. Oh, there it is. Okay. So you go to your y equals, you want to put this polynomial, this rational function here. It's 1 divided by, and I'm going to go ahead and actually put, well, I can put the original x squared plus 5x plus 6. X squared plus 5x plus 6 and close those. Whoops. That didn't work. It moves very slowly. Plus 6. Okay, what's so nice about this software package is it shows you the screen, the function screen, the table screen, and the graph screen. Also shows you every keystroke I hit. So now, No, this was something that the math department purchased. Okay, so I'm going to do a zoom standard because it's a pretty small screen, going from negative 10 to 10, and I'm going to hit enter. And there's the graph. So I have a vertical asymptote here and here, but you know what? I think that there should be more to this graph in between here. Should there not?
Yeah, there's a small little one below.
Down here?
Yeah.
So is it because my window is bad?
It may have been because probably because you cut it in as a trinomial.
Okay, so if no, that wouldn't be it. Why can't I see this? Is that the window right there? Why can't I see it? Okay. Okay, so maybe I should do a y min. Instead of a negative 4, maybe I should make it a negative 20. There it is. Okay, now we've captured it. So it doesn't hurt to use your handy-dandy little $100 calculator, okay, to get a vision, to kind of solidify what the graph looks. So this area is like this, and this one's here, and this one's here. That's a really hideous graph. Okay? And you know, if they asked you questions over here about the graph, it's not an issue. Over here about the graph, but I promise you, when there's a question about this graph, it's always going to land around the vertical asymptotes where there's issues, where there are problems. Okay? Now let's take a look at this next rational. Suppose it's this one, x plus 3 over x squared minus 9. Now, you may or may not remember how this one works. Your first thought should always be factor. If I can factor, let's factor. So if I factor that denominator, this is x plus 3 over x plus 3 times x minus 3. Now, we do have a vertical asymptote happening here. Do I have two vertical asymptotes or one? So there's not a problem at 3. There you go. There's a hole in the graph. There's two things that are happening here. First, you note that this binomial is going to cancel with the one on the bottom. But the 3 is a problem. So if you have a reduction, that 3 that causes a problem here is not creating a vertical asymptote, but it's creating a hole in the graph. So anytime you can get reduction, that means there's a hole in the graph at that point versus a vertical asymptote. And there is a vertical asymptote at negative 3. So we have a vertical asymptote at negative 3, but at 3, we have a hole in the graph, not a vertical asymptote. So if you can cancel and reduce, that's where the hole in the graph occurs. If you cannot cancel, that's where there is still a vertical asymptote. So when you graph this one,
Do you think that's
mm-hmm. Yep. Okay. So over here at negative 3, you have a vertical asymptote, but there is no vertical asymptote at 3. There's going to be a hole in the graph. Again, to get a vision of this graph, okay, these two are going to cancel. I was visualizing this wrong. We can still put this on the calculator to get more comfortable. Did I do that backwards? I did. It's like that, right? Darn.
Yeah, it should be negative. Now, vertical asymptote should be negative 3.
Because these two are going to cancel, which means the vertical asymptote, that's correct.
Yeah, so
Y'all make certain y'all correct that. But this is all messed up now. Your vertical asymptote is at positive 3. And this is where there's a hole in the graph. Okay? So, if we want to get the way this works, and I've already done this, is you're going to come through, and right here, you're going to have a hole in the graph. Then it's going to approach the vertical asymptote and drop. And this is the way the graph will look without the scribbly little mistake. There's a hole in the graph there. Okay? So that's what that graph looks like. And the hole in the graph is really hard to see on the calculator unless you really play with the window to get it right. Okay, you have to really play the window. Okay, then if we have another graph, so we go back to f of x again, and suppose it's 1 over x squared plus 4. Now this is a rational, right? Are there any vertical asymptotes? is there ever an issue with this function where there's going to be an undefined situation? If you put a 2 in, do you get a 0? If you put a negative 2 in for x, do you get a 0 in the denominator? No. This one has no problems, okay? No issues, because there's no number that causes the denominator to equal 0. So not all rationals present these ugly situations, but most cases they're going to look at these examples where you have vertical asymptotes and holes. So in this one, because that was a plus sign, you're covered. So not all of them are bad. Okay? And then, of course, we can play with our trig functions. Suppose we have 1 over cosine of x. It's a rational, so again, or it's a fraction. So when you have that, you got to watch your denominators. What in the world is going to cause cosine x to equal 0? Cosine x equals 0 when x, or theta, is what? Pi halves and 3 pi halves, right? And then every time, every revolution. So remember how we used to write this? Didn't we say 2 pi k, or just k times this? Because this is one revolution, but if I wanted to make several revolutions, I could put a k in front of it, multiply it times any constant, which just keeps wrapping it. Okay. Okay. So what does this one look like? This ought to be an interesting graph. Let me see. So you're going to have vertical asymptote at pi halves and at 3 pi halves. Okay. And at negative pi halves and at negative 3 pi halves, right? Lots of vertical asymptotes. What can you expect from a trig function, right? And then it ends up looking like this. And so when we eventually grow into the limits, they're always going to ask you to find the limit where there's going to be a vertical asymptote. Okay, now briefly I want to ingrain in your mind what the basic is of a limit. Okay? Very informally. Limits are not always easy to find, but just what is the basic thing with the limit? What is a limit? Okay? Really what a limit is, and we often lose this, the limit is a y value of a function. The vertical height of a function at an x value. It's a vertical height. It's a y value. And you're looking for the y value. The limit is a y value of a function at a given x value. So they're going to say, here's x. Tell me the limit of the function at this x value, which means tell me the height of the function when x is 2 or something. It's really that simple. But they ask this question when the x value is landing a vertical asymptote or something, okay, where it gets difficult. But really all it is the y value at the given x. So an example would be something like, what is the limit of the function as x is approaching 2? And then somewhere over here, they say let the function be 1 over x. So the function is given as 1 over x, so they're saying what is the limit of the function as x approaches 2? Well, the rewrite of this would be to replace the f of x with its true function value, which over here was defined as 1 over x. So what is the limit of 1 over x as x is approaching 2? Well, this is quite simple. This is a rational function that has a vertical asymptote when x is 0. But they're not asking me anything about 0. They're being very kind to me right now. And so they're saying when x is a value of 2 over here, what pretty much is the height of the function? 1/2. That's it. The answer is 1/2. The limit equals 1/2. Oh, I should have gotten this more on the picture. Okay. So it can be simple. Another example would be, what is the limit of maybe g of x as x is approaching 2? And suppose that g of x is the rational 1 over x minus 2 squared. That's getting ready to be a little more difficult because, of course, that's where there is a vertical asymptote. So we're thinking, oh boy. Well, the first thing you can do is I want you to see both notations. So we can replace the g of x with its true value, which is just 1 over x minus 2 squared. Now, we can't plug that 2 in there because that's presenting an undefined situation, which is where there is a vertical asymptote. So let's visualize the graph of this function. Well, it's going to have a vertical asymptote at 2, but what does the graph look like? Well, the graph is going to look something like this. Okay, so what is the height of the function when the x value is 2? It's infinity. Now, this is a real issue. When you find the limit of a function, your answer is supposed to be a number. Infinity is not really a number. Infinity is like the black hole thing, okay? It's somewhere out there, but it's not a finite number. So they say, and they'll put this in red in the textbook in italic or something, they'll say, the behavior of the limit is that it leads toward infinity. They don't like to actually say it equals infinity. And then later on they say, but for standard purposes, we will permit you to write the answer as infinity. Do y'all see that? So we are going to put positive infinity, but technically the answer doesn't exist because infinity is not a number. But we will go ahead and override that and write that this limit equals positive infinity. Okay, so technically infinity is not a number and technically the limit doesn't exist, but we're going to go ahead and do this, which is normal. Okay, that's pretty typical notation. All right, now this is interesting. Suppose they ask me for the limit and let this function be h of x as x is approaching 3, which means what do you think the height of the function is as x is approaching the value of 3? And let's suppose that h of x equals x minus 3 over x squared minus 9. Well, we already kind of looked at this earlier because we know that this function can be factored. So we have a vertical asymptote, but the vertical asymptote is at -3, not 3. There's a hole in the graph at 3. So when we look at this, okay, we got this vertical asymptote over here at -3, and over here at 3, the graph looks something like this. And remember, y'all can pull this up on your calculator, and it really tends to help if you have a vision. And there's a hole right here. So, we don't have a function value at 3 because there's a hole there. But the limit is really, what does it kind of look like the height of the function is at that point? Not exactly what is the function value, but what is it approaching? You know, what do we project it to be? If we're coming from the left side, about how high is that? If we're coming from the right side, about how high is that? We don't have to know exactly the answer. We just kind of guess. Okay. Okay. So what is that height? How do we get it? We plug the 3 in where? You can't plug it in here, right? You plug it in here. Okay. So if I put a 3 in here, it becomes 1 over 3 plus 3, which is 1/6. And so this answer is 1/6, which is the projected height of the function. It's not the function value because there's a hole there, but it is about this, it's the height of the function in general at that location. So the limit can exist at a hole in the graph. The limit will take on the value of the height of the hole of the graph. Okay, so that's kind of important. Limit can exist at a hole in the graph. Okay, it doesn't always exist, but it can. Okay, here's another interesting situation. We're running out of time. We'll move quite quickly. Suppose we don't have a true function value, but we'll just call it r of x and we'll have a graph of it as x is approaching 1. And here's the graph. It's like a piecewise function. Here's an x value of 1. Suppose your graph comes up to a circle, an empty hole, then it fills and goes to the right. This would be a piecewise function. And that's r of x. Now in this case, when we get to the x value of 1, that's a 1, that's not a dashed line. When we get to the x value of 1, we don't know if the height of the graph is a height of 1 or a height of 2. It's a little bit shady, right? So if the graph breaks, the limit does not exist. Because from the left it looks like a height of 1, but from the right it's a height of 2, and so this isn't good. We have kind of, opposite answers here. So we can't say the limit exists. So in this case, the limit does not exist. Because when there is a break in the graph, the limit does not exist. Okay, if there's a break, the limit will not exist at a break. Okay, and one more case where the limit will not exist, and this will be our last example. Okay, suppose you have, in this case, suppose your function is 1 over x. Well, we know what 1 over x looks like. It has a vertical asymptote at 0, and it looks like this. Okay, now what is the limit of that function as x is approaching 0? From the left, we're heading down to negative infinity, right? From the right, we're headed to positive infinity. So these guys aren't, right, these guys don't agree. I can't tell what the height's supposed to be in that area. So this is another case where the limit does not exist. So if your left and right sides are not going the same direction or to the same location in the height of the function, or if you have a break in the graph, your limit won't exist. But if there's a hole in the graph, but the function stays kind of smooth through the hole, maintaining the same height from the left and right side, then the limit will exist. So that's the basics. The limit is the vertical height of the graph. It's that simple, but it gets kind of hairy when the functions get a little more difficult and more complex. But remember, the foundation is simply that basic. Y'all have a great weekend. We'll finish this recording on next Wednesday.